Okay, I don't know why it's taking too long, but anyway, we'll start the presentation and hopefully it will start at some stage. So as I was saying, we've been doing some other, okay, so it started now, which is good. So as I was saying, I was teaching you about some background information about the critical things we do in a mineral processing operation. So sampling is very critical, needs to be done properly before you send samples for assay. You need to conduct, or you need to know how you do your particle size distribution, because that is probably the only way to measure your crushing and grinding performance. So it actually helps to know and develop a proper method to do particle size distribution. And I also say to keep an eye on the daily operation of a processing plant. We need to know what goes into the plant and we need to know what exits the plant. Okay, so we need to know not only the total material that's going to the plant, but also the actual commodity. If it's a gold operating plant, we need to know amount of gold going into our plant and amount of gold that is being recovered in a plant. That's the only way to know any potential losses during processing. So as I was saying, I'll probably talk a little bit more about comminution and typically crushing for today. And we'll talk about grinding in the next week's lecture. Okay, so as you can imagine, once the material comes to a processing plant, the first thing we do is to do some kind of size management. And we use crushers or primary crushers to be able to do size management, reduce the rock size, and then we can transport that on a conveyor belt, for example, for subsequent crushing and grinding and for subsequent processing. So the main objective of doing crushing is obviously to reduce the particle size, but also to help with managing the handling of the material that's coming to the processing plant. Okay, so in today's lecture, I'll talk a little bit about what comminution is in general and why is it so critical in mineral processing operations, and also how we do comminution. So in simple terms, when we say comminution, we're just talking about reducing the size of particles. From any given size, you can crush the rock or grind the rock, reduce its size into smaller pieces, and that process is simply known as comminution. Okay, so it's just a process of size reduction, and it's done for a number of reasons. As I told you in one of the lectures, we said liberating particles is very critical, because when we do mining in the first instance, you have the valuable and the gangue minerals together in one single rock. Okay, so the first idea of comminution will be somehow to liberate the valuable from the gangue. Okay, then we can talk about separating the valuable, but first we have to find a physical way of separating the valuable from the gangue rock, and the only way we achieve that is through crushing and through grinding. So in this case, if you assume, for example, the black dots in that rock are the valuables, as you can see in that picture, it's locked within the larger rock. So I would need to do comminution. I need to reduce the size of that large rock so that I produce smaller pieces, and hopefully some of those smaller pieces will contain the valuable, or at least they will be made, the majority of them will be made from the valuable portion, and I will also produce some rocks that are purely made from the waste rock. So once I then create this, I can talk about finding a means, a separation method, to then isolate the valuable and then reject the gangue or the waste material from it. So that's the whole point of performing comminution or performing crushing and grinding. So in general, we want to produce controlled particle size. For example, when you do mining or when you do just blasted ore, you may produce a rock that is 1 meter in size or 1.5 meters in size. So that is what comes to a processing plant. So that is very difficult to move. So we need to think about reducing the size to smaller pieces to start with before we even think about anything else. But obviously in other applications, for example, when you're making roads and things like that, you can also use impact crushers to produce rocks that can be used for road making and so on. Okay, although this is not really the focus of our course, crushing can be done for other operations such as road making and building materials and so on. In mineral processing, the main purpose of comminution is either you want to produce a large surface area on particles, so that's achieved through size reduction. So if I have a rock, I then crush the rock into 100 small pieces, then the surface area of those 100 pieces is actually larger than one single rock. Okay, so by crushing or by grinding, you produce new surface area, okay, because you're producing new small particles, and that's simply achieved by breaking the particles into 2 pieces, 4 pieces, 10 pieces, and so on. So every time you crush something, you produce new surface area. So obviously, one of the main purposes of comminution is increased surface area. Why do we need to increase surface area? Because, for example, if you do leaching, in leaching, we actually put particles in chemicals, and we're trying to dissolve the valuable commodity like copper, gold, or nickel using chemicals. And if you have high surface area, it means those particles are exposed more to the chemicals. So producing large surface area is actually very critical in mineral processing. For example, in process like flotation, surface area is again very critical because when we do flotation, particles are attached to air bubbles, and that is a surface interaction, surface chemistry dominant process. And therefore, again, increasing surface area will help us speed up or at least make the flotation process very effective. And that's why we need to consider increasing surface area during comminution operation. But more importantly though, we need to liberate the target particles from the gangue. And when we say liberating target particles, as I said, target particles or valuable minerals are locked within a waste rock. So we need to first find a way of accessing them, breaking them out, and that's done only through size reduction. So comminution is done typically to improve liberation of particles, create more free particles. Once we produce more free particles made from one mineral, then we can talk about separation or beneficiation after that. So to generalize, in mineral processing, comminution is conducted both to generate new surface area and to liberate the valuable particles or the valuable minerals so that they can be separated from the gangue. Okay, so how do you measure efficiency of comminution? That is actually done by comparing your initial particle size to the product particle size. So if I give you a bunch of particles, you can work out roughly the size or the particle size. And then you conduct comminution, which means you crush them or you grind them, and you produce a lot of small particles with an average given size. Okay, then we can compare the initial particle sizes with the product particle sizes to work out what we call a reduction ratio. Okay, so that's why reduction ratio is defined as particle size of the feed divided by particle size of the product. So obviously when we do crushing and grinding, we produce lots of sizes. So it's not like you crush something, you crush the rock, and you produce only one single particle size. That doesn't happen in nature. So in nature, what happens is as soon as you do crushing or grinding, you produce lots of particles. Some will be very small, some will be intermediate, some will be coarse particles. So you need to have a way of measuring the average particle size to be able to say, this is my product particle size. Or even initially, will I give you a sample to work out the average size? You need to have a way of determining average particle size. And typically for that, we use the 80% passing size, or the P80 that I told you about last week. So when we discussed about particle size distribution analysis, I told you for a given sample, you can do, for example, sieve analysis. From sieve analysis, you can use a number of different sieves in your assessment, and you can determine the 80% passing size. And that 80% passing size can be, for example, used as a way of working out the particle size of the feed or the particle size of the product. Okay, so typically when we work out reduction ratio, we can rely on P80. And therefore, now you gave me a sample, I just do quick particle size analysis on the feed, I crush it or I grind it, and then on the product, I do quick particle size distribution analysis. Then I can determine P80 for both of them. I can work out reduction ratio. Okay, typically when we do crushing and grinding, especially in crushing, the ratio of the feed size to the product size is about 6:1. So in other words, you take a rock, you roughly split it into 6 pieces. Okay, so that's roughly what we expect. So in crushing, we don't expect to produce lots of particles. Okay, in grinding, we expect to produce lots of small particles. So the reduction ratio is a lot more higher in grinding. So it could be, for example, 40:1 between the feed and the product. But in crushing, usually we split particles into only a few number of smaller pieces. So that's how we can assess or measure the performance of a crusher, for example. Okay, so I've also mentioned, I think in the first week, that minerals are made from ordered arrangement of atoms. So basically, they are bonded together through atomic bonds or interatomic bonds. So when we say, for example, pyrite, we know we have iron, we know we have sulfur, and those are bonded together. The iron and sulfur are bonded together in such a way to give the unit cell of a pyrite. So if you wanted to crush or break a pyrite rock, what you're trying to do is basically break the bond between those two atoms. And that can be done either by compressing the rock or by applying a tensile stress. When you stretch the rock, you actually end up breaking the bond between those atoms, and that's how we result in breakage or comminution. So obviously, some rocks are soft, they break easily because the bond, the interatomic bond, is weak. Some rocks are hard because the interatomic bond is strong. And therefore, grindability will depend on how hard or how weak the bond between the atoms is. But also, if you have cracks in the rock, okay, so if you have some pre-existing crack in the rock and you apply some force, it's more likely that the breakage actually goes through those cracks. Okay, so the picture that is on the right there actually shows that if you have a crack in the rock or some failure in the rock, or it could be even grain boundary between one mineral and the other mineral in the rock, it's easier for the stress to propagate through those cracks and break along the side of the crack. And therefore, if you have a rough idea of crack lengths, then you can probably work out how much energy will be required for comminution. Okay, so what are our options to break rocks? That depends on the forces we apply. Okay, so breakage of rocks can be done in a number of ways, and that comes down to the stress we apply to the rock itself. So when we say cleavage or compression, The idea there is to apply just enough force, and that enough force will make a fracture, and basically we're targeting splitting the rock into few pieces. Maybe you have a large rock which is split into 3-4 smaller pieces, and that's the idea of compression or cleavage. If you apply a very high impact force on the rock, chances are you will end up breaking the rock into a number of smaller pieces. And usually those will be randomly broken. You produce small rocks, we produce larger rocks, and there is a wide particle size distribution when high impact force is applied. Okay. If you apply a different force, for example, if the rock particle was rubbing against each other, okay, so we call that abrasion, because the forces applied are parallel to each other, and you end up producing very fine particles, you will still have a large rock intact. That's because abrasion is applied as parallel force, and you end up producing smaller particles, number of smaller particles, but also you will have one large rock remaining. If you apply chipping, so that's at a given angle, so you end up producing smaller rocks, but again the large rock becomes. So for example, if someone asks you to make a tool or some kind of object out of a rock, you actually apply a chipping breakage mechanism, because you're trying to chip different sizes of rocks from a larger material to create a unique shape, and that's done through what we call chipping, or by just making small fragments, by chipping small fragments from a large rock. So why am I talking about all these mechanisms? Because eventually, whatever design you have for your crusher is dependent on the type of force applied. Okay, so when I say, for example, cleavage produces few but relatively large rocks, for example, from one rock you produce maybe 3-4 smaller rocks, and that was done through applying only sufficient force to stretch and fracture the rock. That actually implies that if I wanted this kind of breakage in my process, I need to apply, or my equipment needs to apply this kind of force to the rock. Okay, so eventually when people design the crusher, they have this in mind, because the force that they need to create inside the crushing chamber needs to be just a gentle stress force. Okay, so that's actually how, for example, a jaw crusher works. So when they design a jaw crusher, the force applied is just enough to fracture the rock. The idea there is not to smash the rock into 1,000 different pieces. That's not what we do in a jaw crusher, for example. Okay. If you have an impact crusher, then with impact crusher, the idea is to smash the rock at a very high force, and the idea will be to produce a large number of fragments. So impact crushers are designed in a way so that you can apply a very high stress into the rock, and you basically end up shattering the rock. And for example, if you ask me to make rock for example, making roads and things like that, that's actually how I would probably recommend you to crush the rock, so that you have produced lots of smaller rocks which are now intact, which have also resisted the excessive force that has been applied to them, and they do not have residual crack inside them, and therefore this will be ideal for making roads. But in any case, our operation or our crushing and grinding equipment are based on what kind of force is applied inside the crushing chamber. Again, if, for example, you take a ball mill or a rod mill, they actually apply what we call abrasion force to the rocks, because we add ball or we add rod inside the mill, and those will be in continuous rotation inside the mill. So what happens then is you actually rub the rock against the ball, the steel ball, typically used, for example, in this case, and those are actually parallel to one another. They rub against one another, and therefore you end up producing smaller particles. And basically, when we say grinding, we want to produce large number of small particles. That's why typically in tumbling mills, for example, in ball mills, we actually apply abrasion force. We also apply impact force, but one of the dominant mechanism of breakage will be abrasion force, sorry. So again, the breakage mechanisms for a rock will actually then help us understand what kind of equipment we need to design to be able to come up with appropriate equipment that can be used for comminution. Okay, so now that we have an idea of how rocks break, if, for example, you apply abrasion, okay, as the main mechanism of breakage into the rock, what you will get is large rock and loss of smaller, very small rocks as a product, okay? If you apply cleavage or compression, you produce few number of large rocks. If you apply impact, you produce large number of rocks, okay, but very wide size range. And that picture on the right simply tells you how particle size and quantity of particle size is distributed based on the mechanism of breakage that has been applied, okay? So if I wanted to produce lots of fine particles, I go with abrasion, like a ball mill. If I wanted to produce only a few particles from the original, I apply cleavage. If I wanted to produce a very wide size range, small, medium, and large rocks, I then apply shatter or impact force. Okay, so in the next few slides, I'll talk about the different crushers that we use to result in rock breakage. But I think before I proceed, if everyone or if anyone has a question, please take the time to ask questions now. Any questions so far? All good? Okay, so I mentioned different crushing or rock breakage mechanisms, and some of these are actually exploited in the crusher designs, as we'll see later. But what are the stages of comminution, or what are we trying to achieve when we do crushing and grinding? So as I was saying, if you look at this picture here, this diagram here, what's shown in the x-axis is actually rough diameter of particles for the feed that's coming into the crusher and the product that we're trying to produce from them. So if you look at the primary crushing point there, the rectangle saying primary crushing, you can see that the particles that are fed into a primary crusher may be about 1,500 millimeters in size. Okay, so maybe 1.5 meters in diameter. But after crushing using a primary crusher, the product you want to produce is somewhere around 100 millimeters in size. Okay, so that's the idea of a primary crusher. So once you do primary crushing, maybe the next stage will be a secondary crushing or a third or tertiary crushing. So we can do crushing in 3 stages. We can do crushing in 1 stage, so you don't have to do 3 stages. But if you had a secondary crusher in your processing plant, the idea there will be to go from somewhere around 600 millimeter feed size to produce about 20 millimeter product size. And if you have a tertiary crusher, we go from somewhere around 250 millimeter to a product of about 3 millimeter in size. So you don't have to do 3 stages of crushing, but sometimes you may have very competent rock and could be hard to break down, and it might warrant the use of maybe 3 stages of crushing. But as I said, it's not very common to have 3 stages of crushing, but I have seen places where they use 3 stages of crushing. You may get away with just 1 stage of crushing, where the idea will be to crush the rock and produce somewhere around 20 millimeter product material that can then be fed into a primary grinding machine. Okay, so once you do crushing, then you take the crushed product for a grinding operation. So again, grinding can be done in 2 stages, or it can be done in 1 stage. But most places I have gone to, they use at least 2 stages of grinding. Okay, so a typical progression is 1 stage of crushing followed by 2 stages of grinding. But as I said, this depends on the hardness of the rock and so on. But if you were to do 3 stages of crushing, the idea would be to roughly produce those kind of rock sizes. And that's what I'm trying to show you here. Okay, so typically in crushing, we want to go from somewhere around 1 meter diameter rock, or even more than that, and produce about 20 millimeter diameter rocks. So this is just a rough guide, because some crushers, for example, primary crushers, can just produce 50 millimeter rock, and that can be fed straight to a grinding mill. For example, if you're using a SAG mill or high pressure grinding rolls and so on, that we're going to talk about next week, you can actually still afford to deal with 50 millimeter rock in the grinding stage. But generally speaking, somewhere around 1 meter or more rock size will be fed into a primary crusher and secondary crusher and so on to produce a rock of about 20 millimeter in size on average. And primary crushers that are typically used are jaw crusher, gyratory crusher, and impact crushers. And if you do secondary stage crushing, then you use cone and roll crushers. And in cases where you use tertiary crushers, again, we use cone crusher and roll crusher for tertiary crushing, but usually we use smaller size equipment for tertiary crushing. Okay. So I'll probably talk about some of this in my next slide. So hopefully that become a little bit more clear as we do more of this. So how does a jaw crusher operate? A jaw crusher operates by smashing a rock between a fixed jaw and a movable jaw. Okay, so as you can see in that animation there, on the left you have a fixed jaw, and on the right you have a movable jaw. Okay, so as the rock comes from the feed, it's smashed against a fixed jaw and will be shattered. Okay, so as I was told you earlier, here in jaw crusher anyway, the idea is not producing lots of particles. The idea is just apply enough compression force, reduce the rock into 4 or 5 pieces. Okay, the idea is not to produce lots of particles here. And usually it's done to help us with size management, help us with handling of the rock in a better way, helps us with transporting the rock over a conveyor belt, and so on. And there are different types of jaw crushers. So we have a blade crusher, Dodge crusher, or universal crusher. So the blade crusher, as you can see in that scheme there, it is pivoted at the top, which means it has a fixed feeding associated with it. So we can't vary the feeding rate. But the movable side or the discharge side is open and can move freely, and therefore you can actually vary the discharge that's coming from a blade crusher. If you look at Dodge crusher, it's actually pivoted at the bottom, so you can vary the feed, but the discharge is closed, so it's always fixed. You can't vary that. And the problem with this is sometimes it can choke very quickly because we can't move or vary the discharge end. Universal crushers are pivoted in the middle so that you can vary both the discharge and the feed side of the equipment. One of the more common crushers or jaw crushers is the black jaw crusher, and this one is called double toggle jaw crusher. Let me see if I can use my pen. I hope you can see that arrow there. So in a blade crusher, this is the fixed part, this is the fixed jaw, and this is the movable jaw. Okay, so as you can see, this is where we feed it from. Okay, so this is the feed area, and the idea here is that the movable one is mounted on an eccentric, and on that eccentric you have also what we call a pitman. So as this one rotates, it actually pulls up and down, and therefore the pitman here goes up and down. Okay, so as this one goes up and down, what happens is these toggles here, as you can see, there's one toggle here and there's another toggle here. As this one goes, the pitman goes up, these ones make a straight line, sort of straight line, which means they push the movable jaw towards the fixed jaw. Okay, when the eccentric circulates and the pitman goes down, you actually form like a curve here, which means the movable jaw retracts away from the fixed jaw. So essentially what you're producing is a movement of the fixed jaw staying in one position, but the mobile jaw going sideways like this. And therefore, as the rock comes, it will hit the rock and the rock will be smashed against the fixed jaw. And as that happens, obviously the rock fractures. And because this one is moving away and towards the fixed jaw, once it moves a bit further away, rock falls. And when it comes, rock will be smashed. And that's actually how a double toggle blade crusher operates. Okay, so this can be a bit bulky in construction, but you can have them to move from one place to another, and they can be applied reasonably well as well. So I don't know how clear that picture is for you guys, but this is what a typical jaw crusher will look like. Usually they enclose it in a nice construction, and usually what you see is only this area, but this one is nice and open. So this is where the feed is. So you could have, for example, a truck or something like that feeding the jaw crusher here, and that's where the crushing happens. Okay, just to give you an idea of how big they are. So this is a person standing there, and they can be a couple of story high, as you can see there. Obviously the size will depend on the capacity or the operation size, but this will give you an idea. So once you crush the rock comes through a conveyor belt, goes through most likely a storage, and from that storage you can continue with either crushing again or grinding subsequently. This is a picture I have taken in one of the processing plants around here. So what's happening here is, as you can see here, so this is the inside of a jaw crusher, and this is just an ore which has been delivered to the plant. So it's just blasted and brought to the plant, most likely using a truck. And as you can see, there's lots of fine particles, and also there's some large particles. So obviously this large amount of fine particles shouldn't be sent to a jaw crusher, because there's no point in feeding fine particles to a jaw crusher. It's designed to handle only large rocks. If you're feeding fine particles to a jaw crusher, you just end up limiting its capacity. and you may end up choking the jaw crusher as well. So usually what you do is you put a screen just in front of the jaw crusher. Okay, so the idea here is that the screen then removes most of the fine particles. Okay, so these ones are grizzlies. We'll talk about screens in another topic. But grizzlies are made from very strong steel bars, and as everything comes down through grizzly, the fine particles will pass through, and only the coarse particles will be presented to the jaw crusher. So you can see this picture on the right, and this is just where the crushing happens. So this here is the crushing chamber. Okay, so this is the fixed jaw, and that one is the mobile jaw. So only coarse particles come through, and they will be smashed against the fixed jaw, and that's what we're trying to produce. Okay, so by doing so, by removing excess fines, we are trying to improve the capacity of our jaw crusher and prevent it from choking. And eventually, what you have is a product which looks like this one. Okay, and this is just a picture I have taken on a conveyor belt, which is going to a storage. Okay, so maybe you started with rock size of about 1 meter in size, and you produce rocks that are less than 150 millimeter in size. So you can actually control the opening of a jaw crusher. Maybe you can limit the crushing so that you get only less than 100 millimeter particles, okay, to be produced, or 200 millimeter particles to be produced, and that can be fixed, okay, and that can be determined based on your, obviously, your plant requirement. Okay, so that product size can be controlled by controlling the discharge that's coming from a jaw crusher. Okay, a gyratory crusher is another primary crusher we use typically. Okay, and it works slightly different from a jaw crusher. In gyratory crusher, we have a mantle, okay, and there's a spindle that is suspended on this mantle, and that spindle is on eccentric sleeves. So basically, you apply a rotation. So the spindle goes this way, okay, so constantly does this. So this is a loose spindle, and as you can see here, this is where you feed the particles from. So the particles are fed from here, and this is your crushing chamber, and you have a cone-shaped crushing chamber. So as the spindle goes this way, it actually crushes any rock that is coming in this crushing chamber. So it smashes the rock against the wall, okay, and again, as it moves this way, crushes the rock against the wall again, and basically by moving like this, it ends up crushing the rock, and once the rock is small enough, it will pass through and will be discharged. So slightly different from how a jaw crusher operates, but essentially similar forces applied. So in both jaw crusher and gyratory, we apply a compression force, just gentle enough to crack the rock, produce few particles. So the main difference between the jaw crusher and gyratory crusher is probably the capacity. So if I have a very large operation, say over 1,000 tons per hour, probably gyratory crusher is more suited, because jaw crushers operate for maybe capacity of about 450 tons per hour. If you have a very large operation, then gyratory crushers are more useful, because you can go up to 3,000, 4,000 tons per hour operation. So for large scale, they're more suited. And this is what a picture of it looks like. So as I said, so this is your spindle inside there, and this is your crushing chamber. So basically, as the spindle moves this way, sideways, it smashes the rock against the wall, and that's how we effect in crushing. So what are the main differences between a gyratory and jaw crusher? As I said, gyratory have higher capacity and they're more efficient in crushing, and usually they don't cost a lot to install. the other good point about gyratory is actually this you can bury in the ground. Okay, so you can actually bury this in the ground, which means you can feed them very easily. So they have very good feeding capabilities. But if you look at a jaw crusher, as you can see here, feeding the material to a jaw crusher is not straightforward. So gyratory crushers have better feeding capabilities as well and lower power consumption in general. Again, why do we need jaw crusher? Especially for small operations, they're very ideal. And also if I want to move my crusher from one point in the mine to another place, jaw crushers are a lot more easy to move. So they have easier construction, they can be moved from one place to another very easily, and therefore that can be one of the advantages of a jaw crusher. Impact crushers typically can be used as a primary, but they can be used as secondary crushers as well. And obviously here, the force applied is not cleavage, it is impact, which means there's a very high force applied to the rock, and therefore the idea will be to smash the rock into lots of pieces, and therefore you tend to produce a very wide particle size range. And that's one of the main benefits of impact crushers. So if you want to make a product for making brick or to make roads and so on, impact crushers are by far the preferred ones, because once you apply very high impact force, what breaks will break, whatever resists that force will stay intact, and therefore that's how you can avoid having any residual crack inside the rock, and impact crushers are very good for that. So how do they work? This is the main working principle of an impact crusher. So inside an impact crusher, you have what we call a hammer, and the hammers are actually suspended on a rotor. So this rotor moves at a very high speed, thousands of revolutions per minute, and therefore as the rock is fed from the top here, rock comes and the hammer hits the rock at very high force and hits it against the wall of the impact crusher and basically shatters the rock and produces lots of fine pieces. And that's how an impact crusher operates. And inside an impact crusher, you have what we call the hammer. This is the hammer inside an impact crusher, and this is suspended on the rotor that I've mentioned earlier. Obviously, this is your crushing chamber. So the hammers are actually made from very strong steel, and they can weigh over 100 kilos. And as I said, they rotate at a very high speed, up to 3,000 revolutions per minute. That's why it generates a very high impact. So once a rock is hit by such a large impact with about 100 kilo weighing hammer, it actually shatters the rock, produces large number of small pieces. And you can operate impact crusher at a very high capacity, usually reasonable installation costs as well, and more suited to produce cubic product, as I mentioned earlier. And because it produces lots of fine product, the reduction ratio could be up to 40-1. So basically you smash a rock to about 40 different pieces, and that's what we mean by high reduction ratio. So as I mentioned, for primary crushers, we use either jaw crusher, gyratory crusher, or impact crushers. And again, you can make decisions of which one to buy for your operation based on what you want to achieve. Okay, so they have different advantages and disadvantages. You have to weigh the benefits and the disadvantages of each of them to decide what to do. But in some operations, when the rock is very competent, very hard to break, once you do primary crusher, you might need to do secondary crushing or even tertiary crushing. And for those, we use just modified cone crusher, for example, to be used as a secondary crusher. So instead of having a gyratory, for example, gyratories are large in construction. The spindle is a lot more steep, you can actually modify that a little bit and make or create what we call a secondary crusher. And that secondary crusher is, we call it a cone crusher, but the basic principle of operation is very similar to that of a gyratory crusher. So in this case, the feed material obviously is smaller in particle size. We're not going to feed 1 meter rock into a secondary crusher. Maybe what you're feeding could be about 15 centimeters or 10 centimeters, somewhere around there. And then you can produce smaller particles of about 20 millimeters and so on by using a modified crusher, which can be used as a secondary crusher. So comparing cone crusher, for example, to gyratory crusher, as you can see, the spindle I talked about earlier for a jaw crusher, a gyratory crusher, is very steep. It's thin and long, but for cone crusher, it's actually wide and less steep. Okay, the movement is the same, the working principle is the same, but the inside of it, the crushing chamber, is slightly modified. So in this case, the spindle moves at a very high speed, okay, at higher throw speed, up to 5 times more than the gyratory crusher. And also we have at the discharge end, if you look there, at the discharge end, there is actually sort of less steep and a parallel zone. So here, this one is a bit longer. This is just to help the rocks to be impacted more in bore so that you produce lots of fine particles. So we actually present this opportunity for the rocks to be smashed for a number of times so that we produce smaller particles. So that's why cone crusher is more suited for secondary crusher in comparison to a gyratory crusher, which is larger in construction. And also the idea is just compress the rock enough so that you produce small number of pieces. If you happen to see one, this is what a cone crusher will look like. So inside it is the crushing chamber, obviously, and again, you can feed them using a scalping screen and so on. And they're smaller in construction compared to a gyratory crusher. Another secondary tertiary crusher that's used in mineral processing operations is the roll crusher. So with roll crusher, we have 2 rolls. Okay, so these are made from large metal cylinders and they move against each other. So they're rotated against each other and feed comes from the top. Okay, as they rotate each other towards each other and feed comes through those 2 points, what happens is the rolls nip the rock between those 2 rolls and they apply a squeezing or crushing force to it, and rocks will be shattered, impacted upon, and it will fracture and produce lots of smaller pieces. Now, you might think that maybe this kind of roll crusher may choke very quickly. Why is it not choking very quickly? If there's a choking happening, actually one of the rolls is spring loaded, so it can actually retract back, and therefore whatever is stuck between those 2 rolls will fall, and then the process continues again. Again, with roll crushers, the idea is not to produce lots of fine particles. Maybe your reduction ratio is 4:1. Maybe the impact is just enough, produces about 4 or 5 rocks, and typically that's what you would expect. And they're not very common in comparison to, for example, cone crusher. Almost in many places that I went to, I find cone crushers to be very common for secondary crushing. But roll crusher used to be an older technology that used to be common in the past, but not these days. Actually, we have what we call a modified roll crusher. They're called high pressure grinding rolls. These days they're used for grinding rather than actually crushing. I'll talk about high pressure grinding rolls next week. But the idea here, the modified roll crushers made the rolls really large, so that as you make the roll large and large, you actually increase the nipping force or the crushing force applied to the rocks. Actually, the modified ones apply very high force, produce a significant impact and stress on the rock, and they produce lots of cracks on the rock, and that's why they're more suited for grinding rather than crushing. So as I said, I'll talk about those next week, so probably shouldn't spend time talking about them now. So a little bit of modification on the roll crusher. You can actually have a toothed roll crusher. So with a toothed crusher, what you have is instead of having a smooth roll, okay, you can actually make some structures on the roll like a tooth, and you can apply those, okay, and can be used as a crushing as well. And if you have something like this, if the rolls are modified, then they're more suited for coarse particle crushing, while the smooth ones are more suited for fine particle crushing. But the principle, everything else, is the same as the primary roll crushers, sorry, the secondary roll crushers. And this is just an example of a smaller scale roll crusher. So that is where the crushing happens. That's where you feed the material, and you have two rolls going against each other. And as I said, if you have any choking or anything like that associated, one can be spring loaded so that you can avoid choking. And there are lab scale equipment for roll crushers. I haven't seen actually a large scale industrial size roll crusher, but a smaller scale lab scaled ones are common in some labs. Okay, so what are the progression of crushing? As I said, you could do crushing in 3 stages, but that depends on the hardness of the rock and the requirement of your typical plant. If you're to use 3-stage crushing, then you typically have a primary crusher. For example, a gyratory crusher is shown here. Product goes to stockpile and then screened, and the fine particles can be sent to milling. The coarse particle can be sent to a cone crusher, for example, where you do secondary crushing. Again, fine goes to milling. Coarse from secondary crushing can be sent to tertiary crushing. Again, smaller cone crushers can be used for this application, and whatever comes from the cone crusher as a product can be sent for milling, and the coarse portion from a tertiary crusher can be recycled back, and therefore you can operate this in closed circuit. Okay, so how many stages of crushing you will do will depend on hardness of the rock, will depend on the final product you want. It's also dependent on the size of your plant, how much ore you're producing or processing per day, per year, and also the initial size of the rock. So people using different techniques of blasting or different techniques of mining will end up producing different size rock, and therefore that different size rock can be crushed and ground in different ways. So again, whatever product comes to the mill will also dictate what kind of crusher or mill that you're going to use. But generally speaking, 3-stage is less common. In many places, especially in gold operations, people actually use 1 stage of crushing and 2 stage of grinding as the typical progression. But that's not to mean that's the only method, but you can have 2 stages, 3 stages of crushing, again, depending on what is being processed. Okay, so I will talk about theory of comminution a little bit, but before I do so, if anyone has a question, please ask now.
I have one question, sir.
Yeah.
Okay. Can you hear me?
Yes, I can hear you, Adisu.
Yes, yes. We have different type of crushing.
Yeah.
Um, as we see so far. But my question is how we can know the efficiency of each crushing. Um, how we can measure the efficiency of the crushing, and also I like if I know the prices of the crushers, because the economy is very necessary.
Hmm.
Crushing takes big costs.
Yep.
So to minimize or optimize our crushing cost, we have to know the efficiency of the crushers
Hmm.
and as well as the price of the crusher. Also, maybe the suppliers also, the true
Mm.
suppliers of these crushers, how we can access. That is my question.
Yeah, thanks for that. So to work out efficiency of crusher, it's not actually very critical for crushers because usually what you do for crushing is you set the discharge size. So for example, if I use gyratory or jaw crusher, I will say 100 millimeter is my discharge. Okay, so anything that is more than 100 millimeter will be crushed, and only particles that are less than 100 millimeter will pass through my crusher. So I will set it up like that. So I know whatever I feed to my crusher will be smashed and produce 100 millimeter particles. So efficiency is not very critical for crusher. It's more critical for grinding, but for crushing, it's very predictable. So because it will be dictated by whatever comes as a discharge. Okay, I hope that makes sense. And one of the critical factors for crushers is actually the capacity at which you operate. So if I say this crusher is this size and I need to operate it at 500 tons per hour, then that will be the way I assess my crusher. So if the capacity is significantly lower than that, then it's probably more to do with the feed composition rather than the crusher itself. Okay, so in other words, to maximize efficiency of crushing, we usually work by making sure we feed the appropriate size of rock at a regular interval, and that will be dictated by the initial screening that you do. Okay, if that's not effective, if you're not feeding enough material to the crusher, your capacity will be low, and that's probably the issue when it comes to crushing. So as I was saying earlier, to assess efficiency, you can use initial product size and final product size, but that's more true for a grinding operation. Efficiency for a crushing operation is usually whatever comes through, I set it up to my discharge size. Once it passes through that, I am fine with it. So it's actually a lot more straightforward. In terms of what kind of crusher or what size of equipment we're going to use, that's actually dependent on my capacity. So if I am dealing with, say, 2000 tons per hour operation, your choice is actually very limited. So you have to probably go with a gyratory crusher because all the other equipment are not going to handle a large capacity. Okay, so if my capacity is like 100 tons per hour, then I'm not going to buy a gyratory crusher because that's too expensive. Probably a smaller jaw crusher is more suitable. So what I'm saying is at the end of the day, it comes down to how big your process plant is. Okay. And based on my processing plant capacity, I already can work out which one is more suited. But in terms of crushing capability, in terms of handling rock hardness and so on, both gyratory crusher and jaw crusher are actually very effective. Okay, they can be applied for different type of rock, soft or hard. Yes, there are some things that I need to be careful during operation. So those are operational challenges. Like for example, if I have clays, if the rock is wet and things like that, they can actually make problems during crushing and grinding. But those are operational challenges. They are not associated with the equipment itself. Okay, so in both cases, whether I use jaw crusher or gyratory crusher, I need to handle the operational challenges properly. But working out efficiency, deciding which equipment to buy is actually a lot more dictated by the circumstance of the company and the operation, how big the operation is. Okay. But in terms of suppliers, I'm not probably going to give you one or two. which one is the best or which one is not. This is probably something to do with everyone doing their own research. There are some reliable suppliers here in Australia that provide this equipment. Once they provide, they give you maintenance advice and so on. Okay, this is a continuous assistant associated with each equipment. But obviously, some of these suppliers may not operate in other countries, so it may not be reasonable to actually say this is or that is the best supplier. Okay. But in terms of capital, yes, capital significantly comes in question when you decide to buy a crusher. But in terms of running cost, in terms of energy consumption and so on, you have to be critical more on the grinding side, not the crushing side, because crushing doesn't take a lot of energy. Actually, it takes less than 10% of the energy during consumption. More than 90% of the energy is spent during grinding. Okay. And I'll talk about grinding next week. Maybe then we'll talk about some of the equipment that we use for grinding as well, such as slag mills and so on. Probably that's more appropriate to mention there. Any other question, guys?
Yes.
Yes.
የኔ ጥያቄ on the three types of crushing,
Yep.
primary, secondary, and tertiary.
Yep.
In the previous section, as Dr. Abubakar in processing technology course,
Yep.
he taught us primary crushing is able to crush materials having a pitch size of 1,500 millimeter up to 300 up to 150.
Yep.
That said, primary crushing is up to 600 millimeter size.
Mm-hmm. So you're talking about this one here? This one?
Yes.
Yep. So again, you need to be careful that these are not very strict. So for example, when we say typically what we feed into a primary crusher is, so this is in millimeters. So this is about 1.5 meters is what comes to a primary crusher. Ideally, what you want to produce is somewhere around 100 millimeter rock. But as I said, this depends from operation to operation. Okay. So for example, I know local processing plants which crush the rock during using a primary crusher to only 200 millimeter size. Okay. Then they will use another crusher to reduce it further. Again, that secondary crusher may take 200 millimeter rock instead of 600 here. So the operation is actually 200 millimeter and produces a rock of about 5 millimeter. So this is only a guide, very rough guide. It's not to mean that strictly this is what we need to be doing. Because, for example, when I say roughly 1.5 meters rock is fed into a primary crusher, it depends on the mining method you have done. It's possible that, and it depends on the nature of the rock. When you do blasting, some rocks or some deposits may produce fine material already. Maybe even to start with, you might start with rocks that are 500 millimeter in size. Okay, so that will be what goes into your primary crushing. So it's not necessarily that you produce more than 1 meter rock. You may even, as a primary crushing point, you might start with 0.5 meter size rock. Okay, so these are only general guides. They're not strictly to be, this is what a primary crusher should do, or this is what a secondary crusher should do. Okay. Also, as I said, I don't have to do 3 stages of crushing. I could actually end up maybe only 1 stage of crushing. In that case, maybe the crusher can handle material from about 1 meter in size and produce 50 millimeter rock. Once I produce 50 millimeter rock by just 1 stage of crushing, I don't need to do 2 stages of crushing. I can just feed that into my primary grinding mill. Okay, so again, these are very flexible variable numbers, and they depend on operation. They depend on the nature of the rock, which means the hardness of the rock, and the mining method used. They depend on a number of factors. Okay, so these are just guidelines. Even for example, primary grinding, instead of 50, that's what I said here, we'll start, so 50 millimeter, but you might feed 5 millimeter to your primary grinding mill, okay? And that may produce, so 0.3 millimeter is about 300 micron, but my primary grind may actually produce 100 micron or 0.1. So again, these are very variable numbers, so they depend from operation to operation. Okay, does that make sense?
Yes.
Yep.
And my second question is on the case of impact pressure,
Yep.
mostly in producing the construction materials such as the aggregates,
Yep.
especially for road making,
Yep.
they need an aggregate having a different size.
Yep.
Mostly, as you said, impact pressure is able to produce materials with different size products.
Yep, true.
Isn't it possible just to produce materials having different sizes as much as impact pressure can produce? I mean, isn't it possible to produce materials having different sizes using jaw crusher, cone crusher, and other different crushing equipment?
So
like-
yes,
Impact one?
so it is coming down to the method that we apply, so the force we apply basically to the rock. So in jaw crusher or in gyratory crusher, we're not hitting the rock with high force. So it's a very gentle force, but that gentle force is enough to fracture the rock into few pieces. So we're not smashing it with very high impact. That's why we produce only a small number of rocks, but those small number of rocks are relatively large in size. But with impact, we actually apply a very high stress to the rocks. That's why we're basically shattering the rock into many pieces. So once you do that, what happens is usually you produce different size distribution. So as I said, you produce fine, coarse, and intermediate particles. And those are wide in particle size. And therefore, if I want for road making, for example, I smash the rock, produce large pieces of rock, and then I have to do screening to work out the best range of particle size I want to use for road making. So usually what they do is they screen. They actually use both the coarse and the fine. So the fine is usually the one that can go for road making. The larger rocks can be used as building blocks, okay, for making buildings and so on. So at the end of the day, it just comes down to impact crusher applying very high force, shatter the rock, produce lots of pieces. But the good thing about that is once you smash it, if the rock have been smashed with high impact and they're still intact, that actually means that they don't have any residual fracture inside them. Okay, so that's the main benefit of impact crusher. And if they don't have cracks and so on inside them, then that can be used for building blocks. Okay.
One more question.
Yep.
Can you make it the next slide?
Next slide.
Yeah.
This one?
Yes.
Yep.
Some groups, the size, the crushers according to the size of the product. In
Yep.
5 groups. They classify them in 5 groups: primary, secondary, tertiary, fine crusher, and special crusher.
According to the size.
Yeah, they produce.
Yeah. So yeah, I think this classification is mainly based on how they can be used for what purposes. Again, mind you, here, final product size is only a rough guide when it comes to a crusher. When it comes to milling, grinding operation, final product becomes critical. But in crushing, it is more to do with producing manageable size. We're not even measuring the particle size distribution of the product usually. So I haven't seen any operation here who measures the product particle size that comes from a primary crusher or a secondary crusher. It's more to do with managing the size, okay, rather than being very critical about the product size. So my classification here is based on purpose. So when I say primary crusher, it means that is the initial stage of crushing. So there's no crushing done prior. So once you do mining, you do primary crushing. That's the first stage of crushing. And as I said, in some operations that may be adequate. So you may not need to do any additional crushing. So you may actually feed the product straight to a grinding mill, okay? Because all I need to do is to say, okay, I want to produce less than 100 millimeter particles, and then I can feed this to my grinding mill. So whatever is under that less than 100 mil, maybe majority of them are under 50 millimeters. I do not really focus too much on that. I just focus on the top size or the largest rocks, because what I want to do is feed this into my grinding mill. Okay, then all I want to control is the largest rocks or the top sizes for each. So this classification is based on the purpose of crushing and how that can be used. So basically, once I do primary crushing, if I'm not feeding it to straight into grinding, I could do more crushing. Then for that, what I will use is maybe smaller equipment, because the size now has been reduced to smaller rocks. So my equipment also needs to be smaller, because I can handle smaller rocks using smaller equipment. Okay. Again, with tertiary crushers, you could use cone crusher as a tertiary crusher, or roll crusher as a tertiary crusher. But again, they will be smaller in construction compared to a secondary crusher, because I have reduced the particles to smaller sizes. Then I can then use smaller roll crusher or cone crusher as a tertiary crusher. Okay, so eventually the idea will be as a rough guide to produce these particle sizes during primary, secondary, and tertiary crushing. But again, as I said, it's not really strictly to produce one particular rock size. So for example, for my primary crushing, if I was using jaw crusher, the same jaw crusher can be used to produce 50 millimeter rock as a product, can be used 100 millimeter rock as a product, or can be used 150 millimeter as a product. So the same jaw crusher or gyratory crusher can be adjusted at the discharge end to produce different products. Okay, so that's why the final product can be managed or changed just by using one equipment. So that's why we can't strictly follow the final product as a way of classifying them into different scenarios. Okay, so for example, if I was to ask someone to operate a jaw crusher or a gyratory crusher, I will tell them, please set the final discharge to 100 millimeters. Okay, which means we only allow rocks of 100 millimeters or lower to pass through the discharge. Or maybe something happened, maybe you modified your grinding mill, maybe you bought a new grinding mill that can handle coarser particles. So in that case, I may come back and say, oh, actually, let's modify the crusher so that we can now allow 200 millimeter particles as a discharge. Okay, we can set the same equipment so that we can produce different product, and that can be done in many of those primary crushers. Okay. Any other question, guys? Okay, so if no questions, I will proceed to the next point. Okay, so people have been trying to come up with a number of ways to measure energy spent during crushing and grinding. Some of these theories are actually over 100 years old, okay? But we haven't modified them significantly even to this day. Those theories are actually applied and they're still relevant. But the whole point of comminution theory is to work out energy consumed during crushing and energy consumed during a grinding operation. And there are a number of studies that are being conducted to actually measure how much energy is spent in a processing plant. So in a processing plant, for example, so not considering, for example, what happens during mining and so on, even during processing, you have crushing and grinding, you have separation, which involve either gravity separation or magnetic separation or and so on, flotation, you have leaching, you have lots of other processes, electrowinning, solvent extraction, and so on. So although there are a lot of processes, actually people have done surveys and they found that about 50% of energy is actually consumed during crushing and grinding. So from a processing plant point of view, your crushing and grinding is going to take at least half of the energy required. So that's why people are being keen to come up with different way of estimating energy consumed or power consumed during comminution. And that's some of the theories that we're going to be looking at for today. So you can measure the grindability of an ore, or you can measure how much power is consumed to grind an ore based on what we call bond work index or work index. And work index actually tells us the ease of grindability of a rock or an ore. And typically, when you look at all samples of rocks from many areas, you could say during comminution, maybe you consume somewhere between 10 and 20 kilowatt hour per ton of ore. Obviously, some take less than 10 kilowatt hour per ton. Some take up to 40, 50 kilowatt hour per ton. But on average, in many places, most ores require somewhere around 10 to 20 kilowatt hour per ton. When you look at this, during crushing, actually only a fraction of that is consumed. Okay, so about say 0.7 to about 3 kilowatt hour per ton is consumed during crushing. Grinding takes the majority of the energy. As I was saying earlier, less than 10% is actually consumed during crushing. The majority, more than 90% of energy is consumed during crushing, during grinding. Why is it the case? Because when you're trying to crush the rock into smaller pieces, grinding a small rock to produce even smaller rock is actually energy intensive. So in other words, as you make particles smaller and smaller and smaller, you actually need more energy to break them into smaller and smaller pieces. Okay, so this is the intrinsic hardness associated with grinding. Okay, as particles become finer and finer, they require more and more energy. So that's why during crushing, we do not produce lots of particles. We just reduce particles into a few number of smaller pieces. So that's why the energy consumed is actually not a lot. But in grinding, you do need a lot of energy. So also that's why I was arguing earlier that efficiency and working out power is not very critical for crushing. It's actually very critical for grinding because that's where most of the energy is actually consumed. Okay, so when people think about managing energy or power consumption, they always think about, okay, we need to minimize any overgrinding during our process. So the idea will be as soon as I attain the required size, I remove the product. That way, I remove the product quick. I minimize grinding and grinding and grinding continuously, which results in over grinding and which also consumes lots of energy. And the other thing people are looking at is actually if I do not need to grind something to finer pieces, then I have to avoid it. So try to remove your mineral as its coarse stage, if possible, okay? So that you don't have to crush it and grind into smaller particles, because we know again, that becomes energy intensive. So one of the things people do is, for example, try to reject the gang early on, okay? So that if I can, for example, get rid of 50% of the gang before I do grinding by using, say, methods like sorting and so on, then it actually helps reduce energy associated with comminution. So these are some of the things people are thinking about to reduce energy consumption during comminution. So when you conduct comminution or size reduction, where are the power consumptions? Obviously, size reduction takes power, but also if you have equipment, like for example, a mill, which is tumbling and rotating, you actually spend energy to rotate that cylinder as well, okay? Or if you're using a jaw crusher to move the movable jaw or to move the spindle, you need to spend energy as well. So energy is spent either during the crushing stage, where the idea is to break rock into smaller pieces, so you spend energy, and also to move the equipment, to rotate the equipment, you spend energy. And that all again depends on how much energy I spend for grinding, will depend on the hardness of the rock, will depend on my initial and my final product size. And especially during grinding, the final product will dictate how much energy I'm going to produce, I'm going to consume during a crushing operation. Okay, so how do we then measure energy spent? We use what we call work index. So work index simply tells you how much energy you would need to require to go from one size of rock to desired size of a rock. Okay, so in this case, as I crush it, I know I'm making it smaller, I know I'm making more surface area, and that actually is associated with more energy consumption. So people already figured that out many years ago, as I said, more than 100 years ago. So you can somehow relate energy that is required during comminution to new surface area that you are producing. Okay, so in other words, if I wanted to produce more surface area by grinding, I will need to spend more energy. So there's direct relationship between surface area created and energy spent during comminution, and that's one of a way of measuring energy consumption. So in this case, roughly, you can have an empirical formula that relates energy to surface area. Okay, so if you consume a given amount of energy E, that can be related to the surface area created S. So obviously, it's not just the energy and the surface area. You also need a factor for the hardness of the rock. Okay, so how much energy I'm going to spend will also depend on how hard the rock is. And for that, to account for that, we have a constant K, okay, which is a function of crushing strength of the rock. So generally speaking, we can use this expression here. So energy related directly to the surface area. So more energy is required to produce more surface area, but also that factor needs to be taken into consideration, and that factor is associated with the hardness of the rock. So soft rock requires less energy, hard rock requires more energy. Okay, so that's actually based on this empirical formula. People have tried to develop different models. So now what we don't know is the relationship between the energy and the surface area. Is it exponential? Is it logarithmic relationship? Is it linear relationship? That is not actually accurately configured, and that's what people are trying to determine. So if n is, for example, taken as -2, Rittinger is the person who developed a model based on that, which applies for coarse particles. And another model by Kick takes n as -1. A more accepted universal model developed by Bond actually takes into consideration that n is about -1.5. And this can be applied over a wide range of particles as well. So Bond developed a model in 1952, and he said, if you remember, I mentioned about some breakage within a rock, some failures in a rock. If you have failures in a rock and you apply force, chances are the rock actually breaks along that failure, along that boundary of crack. And he tried to relate work input or energy required for grinding to the crack that is produced in a rock. Okay, so work input is proportional to new crack tip that has been produced, okay, during breakage. And based on that, he tried to work out the energy required. And from that, he tried to actually work out grindability of an ore. So in this case, n was taken as -1.5. If you integrate that previous equation with respect to ds, you should get that expression there. Okay, energy equals 2 times k into 1 minus square root of p minus 1 minus square root of f. And in this case, this expression here tells me that if I have an initial product size f and a product size p, and that equation was integrated between those two limits, you can actually work out energy consumed, okay, during that breakage mechanism to go from one size to another size. And the energy can be converted into work input. That's why you have the equation at the bottom there. Work input is related to work index. Now, instead of the K there, which I've already told you, K is related to the hardness of the rock. Now we can take that hardness of a rock, which is associated with a particular rock, as the work index. So in other words, if I can measure power consumed during my crushing, I did particle size distribution on the product and particle size distribution on the feed, then I know the W, I know the P, and I know the F. Because if I did particle distribution on the product, I can determine the 80% passing size. If I did particle size distribution on the feed, I can determine the F, which is 80% passing size for the feed. If I measured power consumed during my milling, I know the W. Then I can actually work out the work index, which is intrinsic to that particular rock. Okay, so again, this can be a rock from the northern part of Ethiopia or the eastern part of Ethiopia or the southern part of Ethiopia, and the different samples, and someone is keen to do a gold mine at one place, they can actually get an idea of how much energy they're going to require for comminution. How? Because they can work out the grindability of their ore based on just simple tests like this one. Okay, so measure power required to go from one point to another, so to break a rock from one size to another, and work out its grindability, which is related to its work index, and then you can predict how easy or how hard it is to break the rock. And with that, you can also think about how much energy you're going to require doing comminution. Okay, so if you did that, if you determine that, this is called Bond work index, or WI, and this is a very standard method that we use for working out grindability of an ore. Another theory was developed by Rittinger, as you can see, a while back, And in Rittinger's equation, it was stated that the energy consumed in size reduction is proportional to the area of new surface that you have produced. So earlier, if you remember, we talked about energy is related to surface area. So that's what this one comes from. But also we know as you produce more and more surface area, that's related to creating smaller and smaller and smaller particles. Okay. So if you started from 1 kilo sample, you can roughly work out the surface area of 1 kilo sample. But as you grind it and grind it and grind it to smaller pieces, what you do is actually create more and more surface area, because when you break a rock, you produce fresh area. When you break it again, you produce fresh area. So energy consumed should be dependent on new surface area created. But we also know surface area is inversely proportional to size, because we're making particles smaller and smaller to increase their surface area. So then what he did was surface area is inversely proportional to particle size, or in this case diameter. So if you take n to be -2 in Rittinger's equation, you actually get this expression here. Okay. And from that expression, if I have an initial particle size and final particle size, it can be related to obtain this equation here. Okay, so because this one is -2, I think Zacho is having an issue with connection. So if you use n as -2 here, this whole expression becomes minus. So I think you need to switch the final and initial product sizes between these two equations. But in any case, if again I measure the product size and feed size, and I measured the E, which is energy consumed or power consumed in my equipment, I can actually work out the K. Again, K tells me grindability of the rock. Okay, or in other words, I want to predict how much energy I require during the comminution operation, and that can be worked out using Rittinger's equation. Okay, Kick's equation is mainly relating to the fact that energy required is proportional to the volume of particles, or reduction in volume of particles. So again, as I make particle smaller and smaller, as I said earlier, I produce more surface area, but the volume of the particle generally decreases. And therefore, in this case, n was taken as -1, and that expression there was found. So if you look at this one, it says E, energy required, is actually dependent on K and logarithm of final product and feed product and final product. Okay, so here it says as long as you know the ratio of feed to product, you can actually work out grindability, which probably may not be as accurate. Okay, because it states energy requirement depends on the reduction ratio, doesn't depend on the initial and final product, which probably may not be accurate. For example, what it says is if I have a 500 millimeter particle and crushed that into 100 millimeter, the reduction ratio is 5. If I take 100 millimeter size particle and produce 20 millimeter particle, again the reduction ratio is 5, but it is saying same energy is required to go from 500 to 100 and from 100 to 20 millimeters, which probably is not the case, because as you make particles smaller and smaller, you actually need more and more energy. I can already tell you, you probably need more energy to go from 100 to 20 compared to 500 to 100, although the reduction ratio is the same. So again, that's why it may not necessarily apply, especially for coarser particles. And therefore, if you wanted to use a model that may handle a wide range of particles, then Bond equation is by far one of the most dominant ones. And there are standard procedures which are developed to determine Bond work index for rock particles. And in your lab practical, I was hoping maybe you can actually calculate that for a given sample. So for my students here, we actually take sample in the lab, use Bond's equation and Bond's method to work out grindability. So at the end of the day, for a given sample, you might determine bond work index to be 10 or 12 or whatever the case may be. And that can be done in a proper lab, okay? But whether you can do those in your lab there or not, we'll see. But at least I just want to tell you that this is a very standard method that is applied to work out grindability. So what are other methods? So people have come up with a number of methods to help us work out one work index, which equates to grindability. And those can be done either taking individual rocks and estimate their grindability, or take a sample. So a sample could be, say, for example, 100 kilos of sample made from small particles of rocks, and that can be taken, that bulk material can be taken, and grindability can be calculated on them. So if you're using individual rocks, you're probably measuring crushing, okay? If you're using fine particles, you're probably measuring grinding efficiency or grinding rate. But in any case, in the lab, there are methods such as the Bond pendulum crushing test, JKMRC drop weight test. So JKMRC is one of the institutes here in Queensland, in Australia, who developed a method for crushing. Bond ball mill grinding test and Bond rod mill grind test can be also conducted to determine grindability as well. So these are standard methods which you can find in many textbooks, and some labs can actually conduct these tests for you to determine ability to crush or grind rock. So we'll just quickly go through each of them, okay, before I conclude. So with the pendulum test, it's typically a crushing test, and what you have is you take a single rock unit and you try to smash it between two hammers. Okay, the hammers are actually suspended on two large wheels which go opposite to each other. So basically you will lift the wheel, you will lift the hammer, and you put the sample in between them. And these hammers are of specific size and the wheels are of specific size. They are of fixed distance between them according to this Bond method. So the Bond is the guy who came up with the method. So we'll just follow the method and apply the Bond pendulum crushing test. So in this case, sample roughly about 70 millimeter or less in size, or maybe an area of about 15 centimeters square is put between those two hammers and impacted upon. And once you smash it with the hammers, if the rock breaks, then you take it aside and then put another rock. You do the same test, take another rock, same test, and usually you use about 20 rocks, smash them, and measure certain parameters, and you take the average. So what do you measure from a Bond pendulum crushing test? So the hammer mass is known. Okay, you use a standard hammer mass. You can measure the height from which the hammer is dropped. Okay, so if you have a smaller height and the hammer doesn't crush the rock, you can always go higher and crush the rock from a higher height, and so on. So you continue the crushing operation until the rock is essentially shattered. And once you shatter the rock, you can actually record some things. For example, you can measure what we call the impact crushing strength, which is given by the mass of the hammer multiplied by the height of the hammer divided by D. D is the thickness of the rock. Okay, so I do, say, 20 tests like this one on my sample, and I measure the average I, which is crushing strength. Once I do the I can then measure the work index for crushing, which is simply taken by a constant multiplied by the crushing strength divided by the density of the sample, and I get that in kilowatt hour per ton. So the C here is constant. For example, for numerical values, you can take C as 53.49. So this is one of the standard methods developed by Bond based on a set of conditions, known sizes of the hammer and crusher and pendulum test, where you can work out crushing hardness, or the crushing test can be conducted. Once I determine this, then I can say, okay, this is the sample you've given me, conducted a pendulum test, and this is what it comes down to. And this is the size, or this is the number that corresponds to the crushing test I've done. In drop weight test, we do it slightly different. Again, we put the sample. So this is again single rock unit. We put it on a plate, okay, usually on a stage, a concrete base stage, and we drop a weight on the sample. So again, this weight that's dropped on the sample could be anywhere from 20 kilos to 50 kilos, and the height from which this weight is dropped could be up to 1 meter high. So it comes down, smashes the rock, and breaks the rock. Okay, and once you break the rock, you can then work out the energy that was spent in crushing the rock, and can be determined to determine what we call the Bond crushing or breaking energy requirement. And in this case, that energy E is given by the H. That's the height from which this weight was dropped. Okay, and MC here is the mass of the crushing weight. Okay, as I said, it can be somewhere between 20 to 50 kilos, and the M here corresponds to the mass of the sample, which I can weigh. And again, this is individual rock units. Okay, so the height is from which the weight has dropped, so I can work out the energy required, and based on that, we can determine the energy for breakage. Again, this is common in Australia. It's a very common method to determine the crushability of an ore, so that we get an idea of hardness of rock. And not only in mineral processing, this method can be applied for other methods. For example, if you're keen to test the strength of the rock, to determine tensile strengths, things like that, for say building materials and so on, you can actually use this method to work out how much a rock can withstand pressure and impact, and that can be used for other applications as well. So the Bond Work Index is again a standard test that Bond has developed many years ago, and this is again based on a fixed set of conditions. So in this case, you need to use a fixed size mill, so roughly about 305 millimeter diameter and length, and initially you need to crush the rock or the sample to less than 3,350 micron, or 3.35 millimeters in size. Okay, so every rock, every particle should pass through this. Okay, you can use 6 mesh, for example, so that you have 100% passing this size. And then the initial sample you use is about 700 centimeter cube bulk density. So basically, you can use a measuring cylinder, fill the sample up to 700 centimeter cube or 700 millimeters, and then that will be your initial mass. Now you take this mass, you put it in the mill, and you add those ball sizes given here. So these are different size balls, about 20 kilogram in total, made from different sizes, and you put them in the mill. You put the sample in the mill, you start grinding, and the mill is rotated roughly at about 70 revolutions. Initially, you do 100 revolutions, then you stop, and then you remove the product, and then typically you would have a screen size at the end of that. So once I do grinding, I can then use a screen, say 180 micron. Whatever that's smaller than 180 micron will be my product. Whatever is more than 180 micron, I'm going to put it back in the mill. Put it back in the mill and crush or grind again, and again put through a screen. Whatever that's less than 180 micron is my product. Whatever that's above will be ground again. So that's how the process goes on for many cycles. And eventually what you should get is I know my initial feed distribution. I have produced product. I can work out its particle size distribution. PC here is my sieve mesh. So in this case, 180 was what I was mentioning to you. So I can use 180 as a product size screen. So this will be 180. And G here is the mass produced per revolution. So if you see here, I have mill rotating at 70 revolutions per minute. If I measure the mass I produced as a product, I can then work out how much mass or how much grams I produce per revolution. And that can be determined here as a G. Then once you have those, you can actually determine the bond work index or WY, and that can be reported as a figure. So again, you don't need to buy a big mill. You don't need to already install your grinding circuit and then realize how much energy you require. You can actually do these tests prior to buying anything, prior to even having a processing plant to work out feasibility. Maybe the rock is too hard, maybe the rock is soft, maybe the rock is intermediate, but that can be predicted during feasibility studies, okay, by conducting proper metallurgical assessment, and part of that includes grindability, okay? And to do that, as I said, you can use standard methods developed by Bond, for example, apply that, and then that can dictate what kind of grinding mill you're going to buy for your processing plant. And also when we design mills, we actually take into account bond work index and so on to help us understand grinding operation a bit better and also efficiently conduct grinding. So what does the numbers mean? So if I say I have got bond work index value based on that experiment here, let's say you conduct that test and you have bond work index of 20. If you get that, it means that the rock is actually hard, which means you're going to have hard time grinding it, which means you're going to spend more energy for crushing and grinding. Okay. If I get bond work index of say 8, then it tells me that it's actually relatively soft rock. So what does that mean? It means actually I may not need 3 stages of crushing. I do not need 2 stages of grinding. That's too complicated for a soft rock. Maybe I can handle by 1 stage of crushing followed by 1 stage of grinding, and that will be enough for this type of deposit. So you can actually predict those kind of conclusions already by just working out some initial assessment. So that's why I was saying earlier, the circuit for comminution, how many crushing stage or how many grinding stage you're going to have for a processing plant will depend on the nature of the ore. Okay. So if again, there are certain cases, for example, if you look at this table here, in certain cases, the bond work index is actually very high. Okay, it could be about 40, it could be about, even there's mica here showing 135, and graphite here showing about 45. Actually, these ones are not hard rocks. If you look at graphite, if I give you a sample of graphite, you can actually break it with your hand. If I give you a sample of mica, you can easily break it with your hand. Okay, they're not actually hard. What's the problem then? The problem is that they are flat, so you can actually peel them layer by layer. Okay, so if I give you a sample of mica, you can actually peel it layer by layer using your finger, which means when you do grinding, it's actually very hard to grind a flat sample or flat particles, because they simply go through the ball, one ball hits another ball, and not much happens on the actual mica particles. So you don't actually grind them easily. And also when you screen them, because they're flat, they don't pass through the screen very easily. So that's why, based on this method here, they give you a very high work index. In reality, they may not necessarily have high hardness, if you like. So that's why grindability may tell you a lot about hardness, but it's not always telling you hardness. it tells you grindability, which is the ease of going from one size to another size, or from initial feed size to a final product size, rather than tell you absolute hardness. If you want to do absolute hardness, you can do hardness test. You can, for example, do what we call diamond indentation test and other tests that can be applied, okay, which is obviously a different story. But most ores actually have work bond index between 10 and 20, and that's very typical. And already you can tell for those, you can determine already, predetermine if it's a hard rock, if it's an intermediate, if it's a soft rock, based on the bond index calculated. Okay, so I'm concluding my lecture today, but before we do this exercise, if anyone has a question, please feel free to ask.
One more question, sir.
Yes, go on.
I am seeing there is a revolution for the working.
Yeah.
For example, you said 70 revolution per minute.
Yep.
What will happen if this revolution is less or above these numbers?
Yeah.
And also in the case of graphite and micas, because of its flatness, it is very difficult to grind it.
Yeah.
So is there any research ongoing to make machine models to solve this problem, including screening and also ball milling, or particularly for the materials to have like this surface area?
Yep. Okay, good. So in terms of revolutions per minute, so this is, I think I want to emphasize that this is based on a method that Bond developed, and it's more of a standard method. So in this case, for example, mill size was around 305 millimeters in diameter. And he said this is the condition for feed and product size, and this is the initial mass of the sample, and this is the revolution per minute. If you change any of these, it actually affects the experiment. So if I conduct my bond work index experiment at 100 revolutions per minute, I can no longer say I determined bond work index, because I haven't followed the rule strictly, okay? So that's why we need to follow these conditions for operation very strictly. So for example, if I rotate the mill at a higher speed, what happens normally is your grinding mechanism or your breakage mechanism changes. Okay, so as I rotate the mill at a higher speed, the mechanism goes from abrasion, as I told you earlier, to impact, because as the mill rotates high, everything will be lifted in the mill and then drop to the toe of the mill, and then all the ball inside the mill, whatever is inside the mill, will be lifted up and it falls down on the interior of the mill, and it produces high impact. So you can actually increase your grinding rate, but you're not following the revolutions as stated in the method. So your result will be different. But if you keep rotating it to a very high speed, then what happens is all the content inside the mill will have what we call centrifugal force, and everything will stick to the wall of the mill. Because as I said, these are tumbling mills, they're horizontal mills, and everything will stick to the wall, and essentially at a very high speed, nothing happens inside the mill. So everything will move, sticking to the wall, just making circular motion, but no impact, no grinding, nothing happens. So that's why we can't rotate it at a very high speed as well. Usually we have what we call a critical speed for mill rotation, where critical speed would mean that once you pass that critical speed, centrifugal force becomes so high that grinding drops significantly. So that's why mill rotation is very critical. I will actually talk about mill rotation during grinding when we talk about tumbling mills next week. But for this question, at least to answer your question, we have to follow this strictly, because lower mill rotation will have lower grinding rate. Higher mill rotation will bring in higher grinding rate initially, and therefore we may not necessarily have produced bond work index, which was the standard test. We may not directly compare our results to the standard results. Okay, so that can be a problem. Because normally when people ask you to run and calculate bond work index, they will ask you, or they will expect you to follow that rule very strictly. So we can measure the mill rotation using a gynometer or an equipment that a tachometer can be used to track the mill rotation, and that can be done very easily. And your second question was, I forgot your second question now. Your second question was on graphite and mica. Yeah. So with graphite and mica, the issue here is not really because they're hard, it's because the method is not effective for them. Okay, because as I said, they're flat, they're cushioned between the ball, and they don't actually present in accessibility to be crushed very easily inside the mill. That's the main challenge for them. So when you have something like this, people use different methods to maximize, for example, efficiency of grinding. One of the things you can do is maybe you can consider wet milling, so milling in wet conditions. One other issue that you can do is reduce the pulp density, okay? And to improve screening, you can use wet screening, because basically you're trying to force particles to pass through the screen rather than doing dry screening. So there are some strategies that you can use to help with the increasing in grinding efficiency. But as far as the bond work index is concerned, you have to conduct this in dry tests, okay? And what I was trying to do or show you here was to say that although we can roughly estimate grindability of many ores, this bond work index may have its own negative or disadvantages or failures as well, because it may not necessarily work for all samples. It works well for many of the samples, but for some samples like graphite and mica, it actually is not very relevant. Okay, so that's why I wanted to emphasize here. And usually, especially for mica, it's actually very common in many deposits. You can have significant amount of mica, especially in nickel ores, even in lithium ores. You can get up to 20% mica, and that actually presents significant problem. And usually what people do is try to get rid of the mica quickly, like you can do pre-floating or pre-screening to remove the mica first before you actually conduct more fine grinding operation. Okay. Any other question?
Yes, one question.
Yeah.
From the comminution theory, which one is mostly used by the mineral processing industry?
Okay, good question. So for crushing, the drop weight test is very common, okay, especially here in Australia, in the Western countries, it is common. For grinding, the bond work index is very common, okay.
What about for laboratory level?
Yep, so these are actually lab-based equipment, mind you. So we are doing grindability or the crushability of an ore in the lab. So when I say bond work index, these are conducted in the lab on small scale equipment. The drop weight test also uses a specialized equipment, but this is conducted in the lab. So in the big plant, in the commercial large scale, we don't have any methods to use. So basically whatever you use for the big scale operation is something that is already tried in the lab scale. So basically you try bond work index, determine that in the lab, and then you try to use that information to decide or to make decisions in operation of large scale plants. Okay, so that's actually how it works. So basically many processing plants around here, they send samples on daily basis or weekly basis to the labs to work out bond work index of the sample. So maybe that may vary from time to time, from week to week, from month to month, because they usually deal with different ore composition in the plant, and maybe that may affect grindability. So the only way you can check that is by sending samples to the lab and determine the bond work index. And from that, they can see whether the bond work index is increasing or decreasing. And based on those, they can make some decisions in terms of how much crushing and grinding they need to do. Okay. Any other question? Okay, if no question, let's try this example here. I'm hoping it should be straightforward, but let's see. So, okay, for this one, you're going to use this equation. Okay, so the WI is the input, and the W is the input, and the WI is the work index. Okay, so you can maybe copy this one, and you can answer the question afterwards. Okay, so the work input is related to the mill that you are using, and the work index is related to the nature of the rock. So that's the one related to the grindability of the ore, or how hard or how soft the rock is to grind. Okay. So in this case, you're being given the product size and the feed size for both cases. So 300 millimeter to 150, 3 millimeter to 100 micron. Okay, so these are feed product, and you're being given work index for silica. Okay, so in this case, you can say W for silica equals, as the initial expression says, 10 Wi divided by the square root of P minus 10 Wi divided by the square root of F. Now you can determine that because you already know it. You already know the Wi, you already know the P, you already know the F. And then that work input, because I use the same mill, the same operating conditions, so that work input should be the same for the sphalerite as well. Because here You have a spheroid sample and the silica sample. Okay, for the silica sample, you know the work index. You can determine the work input for the mill, and then you can use that same work input, and that work input equals 10 times Wy divided by the product and the feed particle sizes for the spheroid. And then from that, you can determine the work index very easily. Okay, so this side is for quartz based on what's given, and this is W for quartz, and that W is the same for spheroid. Okay, and these are product and feed in micrometers. Okay, so convert the 3 millimeter into micrometer, you get 3000. You convert, these ones are already converted in 150 and 100 micron, so I use 150 100 micron, and the work index can be calculated. So then based on what you have just calculated, work index for spheroid is about 10.8 in comparison to silica, which has about 14. Okay, so you can say that the spheroid ore is softer in comparison to the silica sand. Okay, so you can already predict grinding is probably going to lead to less energy consumption. Okay, and on top of that, you are actually producing finer product, which is about 100 micron compared to 150 micron for the silica sand. Okay. So I'll talk about grinding in the next week, but already some research suggests that actually most of the energy consumed during grinding doesn't necessarily go to rock breakage. It's actually wasted for rotating the mill, and most of it is actually consumed as heat inside the mill. And they say maybe about 2% of the total energy is actually applied for breaking rocks. 98% is actually wasted by the heat inside the mill. I'll probably talk about that one next week. And the other thing I would like to discuss is for next week, I am not available on Friday and Wednesday. Probably from Monday to Thursday, I'll be unavailable. So are you guys available on the Friday of that week? Or do you have classes then? ከሰዓት ይመቻችኋል? በዚሁ ሰዓት መሆን ይችላል? በዛሬው ሰዓት?
በዚህ ሰዓት አለን። ከሰዓት በእኛ 8 ሰዓት።
በእናንተ 8 ሰዓት? 8 ሰዓት ስንት ነው? ሶሪ ተምታቶብኛል። በእናንተ 8 ሰዓት ማለት ማታ ነው? ኦኬ፣ ከሰዓት ነው በእናንተ 2 ሰዓት በእናንተ ማን ነው? ከሰዓት አፍተርኑን ላይ
2 ሰዓት ማለት
8 ሰዓት ያ በእናንተ 2 ፒኤም ማለት ነው። ያ በዚህ ማታ ነው የሚሆነው፣ 7 ሰዓት ነው የሚሆነው። እስቲ ሞክራለሁኝ እንደዛ ለማድረግ አኮሞዴት ለማድረግ። ስለዚህ የሐሙሱን ቴንታቲቭሊ አርብ ከሰዓት በሚለው እንያዘውና ኮንፈርም አድርጋችኋለሁ። ኦኬ፣ ጥያቄ ያላችሁ እዚህኛው ላይ? ሶሪ እዚህኛው ኤክሰርሳይሱ ላይ ነው? ኦኬ፣ የላቡን ዲስከስ አደረጋችሁ? አገኛችሁ ስኬጁል?
ከዶክተር አቡበከር ጋርና ከላብ አሲስታንት ጋር አውርተናል።
ኦኬ። ስለዚህ ይቻላል አሉ፣ መስራት ይቻላል፣ ጊዜ ያለ ምናምን አሏችሁ?
አለ
ኦኬ። ስለዚህ የማግዛችሁ ካለ ንገሩኝና።
ሃይድሮሳይክሎ ክላሲፊኬሽን ግን መስራት አንችልም።
ክላሲፊኬሽን
ሃይድሮሳይክሎ የተባለው እሱን መስራት አንችልም።
ኢኩፕመንት የላችሁም። እሺ፣ ሌላ ምን መስራት ትችላላችሁ? ሁሉንም ትችላላችሁ ሌሎቹን?
ሳምፕሊንግ ሲቫል ራይቲሽ መስራት እንችላለን። ጂኦፕሬሽንም ቦልሚልም አለ።
ኦኬ። ጥሩ። ስለዚህ ለሱኛው ዝም ብዬ ቪዲዮ መላክ እችላለሁ እና ዳታ ልልክላችኋለሁ ለሃይድሮሳይክሎኑ እንዴት እንደሚሰራ አይታችሁ ከዳታው ላይ የተወሰነ ኢንፎርሜሽን ወስዳችሁ አይ ቲንክ ሪፖርት መጻፍ ትችላላችሁ። ስለዚህ ሪፖርቱን ለመጻፍ ታይም ያስፈልጋችኋል። ኤክስፐሪመንቱን ለመስራት ታይም ያስፈልጋችኋል። ሴሚስተሩ አለቀ የሚባለው መቼ ነው? ወይም ደግሞ የሆነ እንደዚህ ሰብሚሽን ማድረግ የማትችሉት መቼ ነው?
ጊዜውን እርግጠኛ አይደለንም። ዘግይተን ስለጀመርን እናነጋግራቸውና ኢንፎርም እናደርጋለን።
ኦኬ። አይ ለእኔ ብዙም ችግር የለውም። ለእናንተ መጨረሻ ላይ እንዳትጨናነቁ፣ ሁሉም ነገር አንድ ላይ እንዳይሆንባችሁ የሆነ ማኔጅ ማድረግ ቢቻል ጥሩ ነው። የሆነ ቀድሞ የሚሰራ ነገር ከሆነ አንድ ላይ ሰሚት አድርጉ። ለእኔ 6 ወርም በኋላም ሰሚት ብታደርጉ ችግር የለብኝም። ግን ዲስከስ አድርጉ። እዛ ያለውን ታይሚንግ ስለማላውቀው ምንድን ነው ያለው የሚለውን ነገር ዲስከስ አድርጉ። አንድ አሳይመንት አለን። አይ ቲንክ እስካሁን በተማራችሁት ላይ ማድረግ እንችላለን። አንድ አሳይመንት ምንድን ነው እሱ? አሁን ኦልሬዲ የተሰጣችሁ ነው አሳይመንት። ከአሁን በኋላ ሪሊዝ ማድረግ ይቻላል አሳይመንት ኦር እንዴት ነው ያለው ነገር? ይቻላል አሳይመንት ሪሊዝ ማድረግ። ኦኬ። ፋይናል ኤግዛም አላችሁ ለሌሎቹ ኮርሶች?
ይኖራል። አብዛኛው ፐርሰንት ግን በአሳይመንቶች እና እንደዚህ በፕሮጀክቶች ምናምን የሚያልቁ ናቸው።
ኦኬ።
ፋይናልም
በቃ ጥሩ። እሺ፣ ስለዚህ ሆፕፉሊ ማኔጅ እናደርጋለን በተባለው ሰዓት። በእኔ በኩል ሌላ ምንም የለኝም። በእናንተ በኩል ጥያቄ ካላችሁ ጀነራል ነገር መጠየቅ ትችላላችሁ። ኦኬ፣
ጨርሰናል። እናመሰግናለን።
እሺ፣ መልካም ቻው።
Thank you.